All right, so let's look at 7.2. And um, if you went through 7.1 and kind of understood that, then we're going to be doing the same thing again in 7.2. So a lot of it's going to be real similar. In 7.2, we were estimating a proportion, right? So we were trying to say something about the population proportion and say that it was ultimately we were trying to create confidence intervals. And so we would say, end up saying, we're 95% confident that the proportion of that the population proportion is between 35 and 45%, something like that. Well, in 7.2, that's where we want to end up, but we want to say something about the population mean. We're 95% that the population mean is between, 65 and 70, but it's a mean that we're talking about, okay? And so we it looks real similar. There's a lot of the same structure, but we have a couple different approaches that we're going to be taking when we're estimating population mean. There are two ways to do this, two situations, and we'll go through each of those situations in these slides. Okay. But mainly we're trying to find ways to use the sample mean to make some sort of inference or prediction or claim about the corresponding population mean. All right. Now we have the same kind of deal. One, we can just use a point estimate, so we won't talk about that much, but we can simply say that take the sample mean, the mean that we got from our sample, and use that as a point estimate for the population mean mu. But ultimately, we're going to spend most of our time on the confidence interval, creating a confidence interval. And then also, lastly, we'll talk about how to find the sample size that we need in order to get to estimate a population mean with a desired error, right? So we want to be this accurate. How many people do we need to survey? All right. So let's look at case one. And this, in fact, is the way that things most often happen. And this is when we don't know sigma. We don't know the population standard deviation, which makes sense because we don't know the population mean, and we also don't know the population standard deviation. So it makes sense that we wouldn't know one or the other. Now, I'll just give you a preview. We're going to look at a real simpler case later where we do know sigma, but that doesn't happen very often in practice. But the first thing you determine when you're trying to find a confidence interval for estimating a population mean is you ask, do I know sigma or do I not know sigma? If you do not know it, then you'll proceed with the method that we're going to talk about here. All right? Okay, so basically we're going to try to just give you the formula, and you see the notation here. Mu is the population mean, n is the sample size, x bar is the mean that we get from our sample, e is the error, and s is the sample standard deviation. Okay, so notice this. We're going to make use of the mean we get from our sample, but also the standard deviation that we get from our sample in this process. All right, now we have a few things that are required. Similar to what we had before, we have to be dealing with a random sample, and we want our sample to be the population either needs to be normally distributed, come from a normally distributed population, or our sample size needs to be greater than 30. If those are the case, if those two requirements are met, we can proceed in this way. Here's what you need to know. The confidence interval that you're going to create is going to look like this. It's going to be your sample mean that you find from your sample plus or minus the error. Okay? What is different is we have a different error formula when we're creating a confidence interval for a mean as opposed to a confidence interval for a proportion. Okay? Other than that, everything handles the same way. So here's your formula for the error when we're creating a confidence interval for estimating a population mean. Now let's talk about it just a little bit. A couple things are familiar. N is the sample size. How big were we using? S is the sample standard deviation. And if you look back to the method we used before with proportions, up here was sigma because we knew sigma. But we don't know sigma. Remember, sigma is not known. So what's the next best thing? Remember, sigma is the population standard deviation. Well, the next best thing to use is the sample standard deviation. So that's why that fits there. Okay, sample standard deviation, sample size. Now, T is a new value for us. We're used to seeing z-scores. Here's the deal. T-scores are just like z-scores, but we use them when we don't know sigma. In other words, if I were to look at a graph of a t-distribution, it's going to look like a lot like a z-distribution. Now, obviously, it's not going to be the same shape, so the numbers, the areas under the curve are going to be a little bit different. By and large, to find the t-scores, we're going to use technology. And so I'll talk about that and create a separate video for you to use and to learn how to use your technology to find the t-scores. There is a table in the back of the book, but it's a little difficult to use. Not impossible. Your lectures in my stat lab will show you how to do that. But that's the big difference. We need a t-score. And just remember this. The t-score depends on two things. It depends on how confident we want to be, just like before. And it also depends on the sample size. Okay? Every different sample size uses a different t-score. And how do we determine which t-score to use? We calculate what's called the degrees of freedom. That's what DF stands for, degrees of freedom. And the degrees of freedom is simply your sample size minus 1. And that will tell you which t-distribution to use. We'll get into that a little more. All right. So the t sub alpha over 2 is the critical value that's separating the area. Just like when we were using z sub alpha over 2. It's separating the area where we have alpha over 2 in the right tail of the student t-distribution. It's called a student t-distribution. Okay. Degrees of freedom is simply the sample size minus 1. All right, we've got some ideas on round-off rules, kind of what we're used to using. All right, when using the original set of data, round the confidence interval estimates to one more decimal place. When using the summary statistics, round the confidence intervals to the same number of decimal statistics. So if we're working from the original data, we'll have one more decimal than the data. But if we're working from the summary statistics, in other words, somebody has come along and told us what the sample mean is. They didn't tell us exactly what the sample was. They didn't tell us the original data of the sample. They told us what the mean and the standard deviation was. We'll use the same number of distributions. Okay. How do we find t-scores? Well, there's our formula for t-scores. It looks a lot like our formula for z-scores. We'll see it as we go along, but there's the formula for t-scores. Okay. Now, degrees of freedom, there's some theoretical things here. Mostly you just need to remember that the degrees of freedom is the sample size minus 1, n minus 1. Okay. All right. The table that we use for finding these critical t values, and this is all that the table does, is it finds the critical t values, is table A3. Okay. So if you look up table A3, and you look across the top of table A3, you will start to see the critical the areas. All right. So you'll see the areas across the top of A3, the area in one tail, and so depending on what your area is, what then that you need. So for instance, if I'm trying to find the 95% confidence interval, then that means the area in one tail is 0.025, right? 95% means that there's 5% in the two tails, so area in one tail is 0.025. And so I would use the 0.025 column, and then I would go down until I found the degrees of freedom that matched my sample, and that will give me my critical t-value to use in my error formula. Okay, we'll use that in some examples. Okay, so as we think about t-distributions, there's a picture of the t-distributions. All right, and you'll notice the standard distribution, the z-distribution, is the green one. And so the t-distributions are just slightly different shaped, which is good because they're very similar to what we're used to using. But because the shapes are different, the areas are different. And so we'll use technology to find the areas under t-distributions. In short, whenever we're answering questions about means where we don't know sigma, we're going to be using t-distributions from here on out. Okay? And you can read some properties about that. Very similar properties to the regular z distribution. I want to get us to some of the examples. All right. So let's look at an example for constructing a confidence interval for mu. That's what we really want. There's our formula for E for the error. And so our confidence interval is going to be the x bar plus or minus the error, or x bar minus the error, right here. So the population mean is x bar minus the error, or is between x bar minus the error and x bar plus the error, just like with confidence interval estimates for proportions. Okay. All right, so let's look at an example. Find the critical value. So we're just going to first look at practicing finding the critical value for t sub alpha corresponding to a 95% confidence interval. So let me draw the picture here. So when I'm talking about a 95% confidence interval, I'm talking about this picture. I want boundaries, bam, symmetrically placed boundaries, so that the area in the middle is 0.95. Well, that leaves the area in one tail as 0.025, and the area in the other tail is 0.025. Why? Because those have to add up to be 0.05. All right? And so that's the value that I'm going to look up in my table. The area in one tail, I'm going to look that up in my table. And so you can see it right here. Here's our table. And it's very small here. Let me zoom in. So there's our table. So remember the picture. In the area, in the tail is 0.025. So here's my table. And so I look up on the top, area in one tail, 0.025. And let's see, what was my degrees of freedom? Oh, n equals 15, right? So I'm going to go down here to degrees of freedom of 14, right here. And use this. This would be my critical t value, 2.145. All right. I guess we'll just leave that right there. So t equals, what was it, 2.145. That's the t that we will use if we're creating a 95% confidence interval when our sample size is n equals 15. Notice if we're using a different sample size, we use that same column, but we'll use a different t value. Okay. So here we go. Because n equals 15, the number of degrees of freedom is 14. And you can see here the work they've done. So the amount of area in one tail is 0.025, just like we saw. And so t equals 2.145. All right. Now, we can also use technology to do this, and I'll create a video to do that. But the technology is going to be really important because finding t values on tables is kind of a pain, because basically you need a different value, a different table, a completely different table, actually 2 pages, just like with our z-score, for every single different degrees of freedom. Okay. So to find the degrees of freedom, let me just write down here what you're going to use. You're going to use on a TI calculator, you're going to use this function, the I in the inverse t distribution. And what you're going to enter is the area in the left tail. So you're going to be entering this area, 0.0, and so in our case we were doing 0.025, comma, the degrees of freedom. All right. Comma, the degrees of freedom. So inverse t, so that INVT stands for inverse t. In other words, we're giving it an area, and it's giving us the t-score. And so, comma, degrees of freedom was 14 in this case, and that should spit out a negative 2.14478, blah, blah, blah. But we round it off, right? And so that's where we get our negative 2.145. Now, of course, that left one's going to be negative, that right one is going to be positive. But use the inverse t distribution. All right. So, that's going to be our inverse t distribution, or that's going to be our critical t value. So we have the same kinds of things. We don't use these two particular formulas. Basically, this first one says that if you've got a confidence interval, you know the upper limit and the lower limit, then x bar, the actual sample mean, is the number sitting halfway between those, sitting right in the middle of the confidence interval, just like it was before. Same way, the error, if we know the confidence interval, then we can find the error, just do the upper limit minus the lower limit divided by 2. We just don't use those very much, but they're the same formulas as we had before. Okay, so let's look at how I'll demonstrate some examples of this, but the last thing I want to show you right here is just the formula for the situation where you need to find the sample size given to meet a required desired margin of error. And so I'll just show you this formula. The sample must be random, but this is the formula you want. Okay, so if you are doing a study and you decide, okay, I want to be this accurate, I want to estimate the mean to a certain error, say 3%, that would be your error, 0.03. Then you ask yourself, well, what does the sample size need to be? And this formula will spit that out. Notice you need to know the z-score. You use the z-score, and then you use sigma, the population standard deviation. I'll show you examples of these. We're just kind of running through so you can get some ideas here. Okay, now, you saw in that previous example, or the previous formula, that you needed to know sigma. But what if you don't know sigma? Well, you can use the range rule of thumb to figure out sigma. So the sigma is approximately the range divided by 4. Remember, range is high minus low divided by 4. So you could do that and put that in your formula. All right. All right, so let's look at an example. Assume we want to estimate the mean IQ of scores, IQ score for a population of statistics students. How many students do we need to randomly select if we want a 95% confidence interval, and we want the sample mean to be within 3 IQ points? So our error is 3, right? So for the 95% confidence interval, we have alpha equals 0.05, right? 1 minus 90.95. And that gives us our common z-score of 1.96. And so we're going to plug that 1.96 into our formula down here, right? And 3 is that we want to be within plus or minus 3. And then where do we get 15? Just look at the discussion of the immediately preceding example. Okay, that's where we get the 15. And you plug those into the formula, and that gives you 96. But you'll always round that up. So you want to survey at least 96. So that means bump that up to 97. All right. All right. So we basically, what we need to do is we need to survey 97 people. And if we do survey 97 people, we'll be able to create a 95% confidence interval that is within 3 points of the true proportion. Okay. All right, let's talk briefly about the second case when we're trying to create confidence intervals when sigma is known. What changes is, well, since we know sigma, we use it in our error formula, right? The only thing that changes is our error formula. And the big change, one big change is that we use sigma instead of S. Okay. The other big change is we use z-scores. Our standard z-scores that we're used to using for finding confidence intervals, we use those. So no t-scores. So that's a really nice and simple change. All right, so let's see how this would work with an example. So suppose we are given the raw data of 15 birth weights of girls. So there are the 15 birth weights of girls, right? And we want to construct a 95% confidence interval estimate of the mean birth weight of all girls, right? So we're going to use these 15 samples to estimate the mean birth weight of all girls, right? That's what we do with a confidence interval. Now, here's what happens. If you're given the raw data, oh, by the way, we're assuming that sigma is known and it is 2.9. Okay, so this is the sigma known situation, which tells us we're going to be using this as our error formula. Okay, now, in this case, we're given the actual data, right? So we actually need to find the sample mean from this. So we'll do that. Just find the average of those 15 numbers. Okay, and you can see that we've met the requirements. The sample is random. The sample size is 15. That's not 30, but birth weights are normally distributed, so we can assume normality and use our approach here. Okay. You can check the normality by actually using creating a normal quantile plot like we did way back at the beginning of the semester. But we're just going to jump right in here. Here is where you will start your work. If you want to create the 95% confidence interval, that means alpha, your significance level, is 0.5. That means if your z-score will be 1.96. Okay, you know sigma, n is 15. You plug all of those into your formula right here, and that gives you your error. Okay, so you're going to add and subtract that error from the average that you found from averaging those 15. 30.9 plus or minus to get your lower boundary and your upper boundary. And that will be your confidence interval. So, like we say, this is not the situation. Knowing sigma is not usually the way it works in real life. Most of the time we don't know sigma. All right? So here's just a little key to remind you which ones to use. I would pencil in here the error formulas, right? So I'd have another, because that's the real big difference, right? So if sigma is not known, then your error formula is a t times s over square root of n. If sigma is known, then your error formula is z times s over, not s. It's sigma, you know sigma, so let's use it, over square root of n. Okay? So those are the big two differences. Other than that, real similar approaches.